Hello everybody and welcome to Kinematics Physics 12. So before we begin, there are some terms that you have to make sure you know. These terms are kinematics, dynamics, the difference between scalars and vectors, position and displacement, average speed, velocity, average velocity, instantaneous velocity, instantaneous speed, average acceleration, instantaneous acceleration, free fall, that's important, projectile, range, projectile motion, frame of reference, and relative velocity. And of course, all of these will be discussed as this course moves along. So let's begin with, what is kinematics? Kinematics, as defined, is the study of motion without considering the forces that produce the motion. If you do consider these forces, then you're talking about dynamics, which is the study of the causes of motion. Scalars and vectors are very similar, but they're very different too. Scalars are quantities that have only a magnitude or numerical value. Vectors have this magnitude, and they also include a direction. Position versus displacement. Position is the straight line distance and direction of an object from a reference point. So you choose a reference point, and you say, from this point, wherever I am, that is my position. If I'm here, this is my position from this reference point. Displacement is the change in position of an object. So position 2 minus position 1 gives you that change in displacement, and it has that vector arrow on top. So how it works, in this diagram, in figure A, we have a puck and it's sliding on the ice. This line right here, that's our reference line. So in position 1, the puck is this far away from the reference. In position 2, it's here, and in position 3, it's over here. So in figure B, you have a position versus time graph. Time is on the x-axis and position is on the y-axis. So this is our reference point right here. And in the first position, we are this far away from our reference. In position 2, we are this far away from our reference. In position 3, we are this far away from the reference. So you can see that we're moving relatively very, constantly. So here we have constant velocity. As time increases, we have constant velocity. Now, average speed is the total distance traveled divided by the total time to travel that distance. Over here, total distance traveled, notice there's no vector symbol over here, so it's distance, not displacement, over time. Velocity is the change in position divided by the interval. So you have displacement here, so change in position is, remember, this thing can be replaced with d2 minus d1. And velocity is a vector, so you have that vector symbol on top. Average velocity is the displacement divided by the time interval for that change, or also known as the slope of a secant on a position time graph. So here you have a position time graph. You have an object which follows this path, right? If this is your reference line, at t1, the object's over here. At t2, the object's here. In between, the object is not following a straight path, but it's following this path. If you want to know the average velocity, you have to use this formula over here. d2 minus d1, which is this d2 minus d1 over the time interval, and you get the average velocity. Of course, also that vector symbol on top because it is velocity. Alright, so let's look at a problem because physics is all about problems. A bus driver begins a descent down a steep hill and suddenly sees a deer about to cross the road. He applies the brakes. During the bus driver's 0.32 second reaction time, the bus maintains a constant velocity of 27 meters per second forward. Determine the displacement of the bus during the time the driver takes to react. Okay, so two key things that were given here. A 0.32 second reaction time, so that's the time interval, and a constant velocity of 27 meters per second. So if you want to find the displacement, you have to use this given formula and rearrange it. So multiply delta t on both sides so that you end up with this formula. And plugging in these values for your constant velocity of 27 meters per second and time interval of 0.32 seconds, you end up with 8.64 meters. So the bus actually travels 8.64 meters in this short reaction time. Let's do another problem. Drivers at the Daytona 500 Speedway in Florida must complete 200 laps of a track that is 4.02 kilometers long. To break the record, a driver has to complete the race in 6.21 hours. Calculate the average speed in meters per second the driver has to maintain. So this is a little more interesting problem. It's a little longer and it has a nice story. So this is how the solution goes. You use this formula to calculate the average speed because there is no vector sign on top. There's no vector sign over here on D either. So we're given laps, kilometers, and we're asked to find meters per second. So we have to convert this to meters. So we say total distance is 200 laps times, in each lap there are 4.02 kilometers. So the laps will cancel here. So we have 200 laps. So we have 200 times 4.02 kilometers. Now in each kilometer there are 1,000 meters, so the kilometers would cancel out. And when you do this math, you get 804,000 meters. The total time is 6.21 hours, and in each hour the magic number is 3,600 seconds. So when you do this math, you get 22,356 seconds. And of course, the average speed formula says take this number divided by this number, and you get your answer. So this is the speed that the driver has to maintain to make that new record, 35.96 meters per second. Moving along, some key terms to remember now. Tangent, a straight line that intersects a curve at a point and has the same slope as the curve at the point of intersection. Instantaneous velocity, the velocity of an object at a particular point, or the slope of the tangent to a position time graph. Instantaneous speed is something similar, only it's the speed of that object at a particular point, and it's the magnitude of the slope of the tangent to position time graph. So we'll get to what this is right now. But let's look at this diagram first. We have instantaneous velocity. As you can see, you have a car here traveling from this reference point at 0, and it's at this position, number 1, over here, and position 2 is over here, position 3 is here, and position 4 is here. You can see that it's going faster, right? We obviously know it's going faster because we see that these dots, there's more space between these dots. So on a position time graph, you say if this is my reference line, and if position 1 is here, it goes here, position 2 is here, position 3 is here, and position 4 is here. We don't have this constant line that we had. We have more of a curve, right? And if we have a curve, that means we don't have constant velocity. In fact, we have constant increasing velocity with time. Over here, the idea of the tangent. You take, this is your secant line, right? You take 2 points and you find the slope between them. If you want to find the instantaneous velocity, not the average velocity. You do the same thing, but then you eventually get to a point where there is no second point. It's that instantaneous point. And that's what your instantaneous velocity is. So at t is equal to 1.5 seconds, there's only one point. If you do that math, you get something like the distance over 0.0000000001. Okay, let's look at this one. In which graph does the velocity increase with time, and in which graph does the velocity decrease with time? So here we have position and time, and we're constantly decreasing here. So if it's constantly decreasing, that means that the velocity is going to be constant, right? It's zero, basically. Well, it's not zero, but it's constant because we are moving. So it's not increasing or decreasing. So it's from these two graphs. Here, we are going farther. This is a reference line, and the position is changing, but we are going farther. But you can see that each time that we go farther, we're going less farther than what we should have if this line were to continue like that. So in that sense, that dip over here shows that the velocity is decreasing. And similarly, here the velocity increases because we should be going like this. But in fact, with time, we have this exponential increase in position. So the next time, we'll talk about some more interesting terms related to kinematics, and we'll start with average acceleration and instantaneous acceleration.